Welcome, everyone, to our evening lecture. This is a special event in that not only are the members of the past conference welcome, but we also welcome the community at large, and also streaming online to the public at large. And so for those of you who are just visiting for the evening, welcome. We're a friendly group. Introduce yourself if you don't mind. We would love to meet you. So welcome to tonight's lecture. I'm really delighted to have Rick Stevens join us. Rick is a professor of computer science at the University of Chicago and the associate lab director of the Computing, Environment, and Life Sciences Directorate at Argonne, and an Argonne Distinguished Fellow. He provides research leadership for really all of the U.S. Department of Energy in his areas of expertise and beyond in computational and computer science, from HPC architectures to the development of tools and methods for bioinformatics, cancer, infectious disease, and other problems in science and engineering. Of particular note in recent years is Rick's outstanding leadership in developing a community strategy for integrating AI and quantum capabilities into the computational sciences. It's my pleasure to welcome Rick to talk with us on the topic of post-exascale computational science and the emerging mix of HPC, AI, and quantum. Please help me welcome Rick to the stage.
Thanks, Mike. You guys hear me okay? All right, great. Okay, so this is designed to be a fun talk and a bit controversial maybe in a few places. And I have a lot of material in here, but the way I'll do this is I will show a lot of slides and I'll pause and have these kind of punctuated summary kind of slides where I kind of annotate my own talk a little bit. And I'm very happy after the lecture to stick around and talk to people and have talk about questions and so forth. So this is a kind of high-level notion of what I'm going to talk about. So there's kind of four things going on, and unlike, say, 20 years ago when we started working on the path towards exascale, we kind of have to do all four of these at the same time this time around. So I'll talk a little bit how we got exascale started, what we still have to do. A lot of you have been involved in that journey. And of course, Europe is starting its own exascale journey, so we'll talk about that a little bit. AI is, of course, exploding everywhere. We're trying to launch a major AI initiative inside the US in the Department of Energy, but other agencies are also doing the same thing. There's a lot of interest in AI, a lot of concern about AI and so forth, and I'll talk a little about how we're thinking about that in the context of science in particular. I'll talk about quantum. There's a lot of investment going in quantum. There's a lot of confusion maybe about where quantum fits into the ecosystem and what timeline it's actually on, and I'll try to clarify that a bit. And then I'll talk about Zeta scale. And Zeta scale is probably the sleeper of all of these things. It's the technology, whatever it's going to be, that's going to underpin the future progress in classical computing, and we kind of need it for everything that we want to do in the future, and yet nobody's really talking about how we're going to do that. So anyway, I'll tie it all together. There's an acronym that we made up back in February. I've given this talk now 3 or 4 times, or versions of it. This is a new version, but we call it EasyQ. It doesn't mean that getting to quantum is easy, but it's to remind us the order in which we have to do things. All right, exascale, then AI, then Zeta scale, and then quantum, and you'll see why in a few minutes. All right, let's talk about exascale. Back in 2007, in the spring of 2007, there was a number of conversations going on about what we should be doing in the US in high-performance computing to continue making progress. And to put this in perspective, this was at the time where we had achieved terascale computing. We hadn't yet achieved petascale computing, and at that time, we were imagining that we have to take a look at what's possible, what might be on the fringe of possibility. And there were two series of workshops and community events that happened in that. One that was in the summer that was really focusing on kind of the application opportunities. At the time, we weren't even sure it was even feasible to think about exascale. And there was another report, a group that got together in the spring of 2008 to look at the kind of feasibility of building such machines. And this kind of kicked off a many-year process, and I'll walk you through that for a second. So starting in 2007 until about 2012, there was actually no program in the US. What there was a bunch of crazies like us running around saying, we need to have a program. We need to figure out how to build these big machines. We need to figure out how to organize the community, and so on. We kept getting support for holding workshops. There were dozens of workshops in that 5-year period, stack of reports this big. And we were slowly building the case. And at that time, there was a lot of resistance, actually, to doing something really large. Around 2012, though, the science case started coming together. And I pulled some slides from the deck back then. We were trying to drive this thing based on progress we could make in nuclear energy or in climate and geoengineering. And you think about this, these were topics from 2007, 2012. Of course, geoengineering is a hot topic today, and climate is a hot topic today. Back then, it was not so clear that these were big topics. Materials by design, if you actually read that little blurb, it sounds like you could have written it yesterday. Combustion was interesting here. At the time, of course, this was before any successful electric vehicles. The thinking was that a huge amount of the energy supply comes from burning stuff, and we better get really good at doing that to minimize impact. And then fundamental physics. And what happened in a lot of these meetings is there were these charts that were produced that had this general notion of up and to the right, okay? Like over time, we're gonna need more and more computing, and we asked people to put down, what would you do if you had 10 times more, 100 times more, 1,000 times more computing? And I have hundreds of these slides. I didn't put them all up here, of course, but just some of them were these up and to the right, some of them were timelines going out even like 25 here. Some were up and to the right, some were lots of up and to the right in biology. I remember making that slide back then. So we made this case. We also tried to lay out what we had to do in terms of building machines. And what was interesting is that we, of course, had been building machines for quite a while. I mean, the Department of Energy Laboratories, of course, been deploying supercomputers for decades. And we had machines on the floor in 2004, 2006, and so on. But we laid out a strategy that was quite unique at the time. So the three of the labs, Oak Ridge, Argonne, and Livermore, got together and decided to hold a single procurement operation. We get 3 machines, but do it all together. These were pre-exascale machines. And we had a timeline here of trying to, say, every 4 years, pushing up the machines, and you can see we had a kind of a landing zone in 2022 for the first exascale machines, but that wasn't like a fixed point, it was just kind of a step along the way. And you can see some of the specifications, and some of these were kind of correct, like the flops, that was easy, memory is harder. I/O buffers, at the time we had this notion of I/O buffers, maybe you could think of that as non-volatile near memory now. Back then we weren't sure what was going to replace, storage disk and tape. It's big things, power budgets and space budgets. But this created a sense that exascale was not a destination, it was just a way stop. At my lab, here's a kind of trajectory. We had been deploying kind of machines for science starting around earlier, quite a bit earlier for parallel computing research, but around for science, and then this scaling up. And to put this in perspective, the exascale kind of conversation started here, program plan kind of started here, and money started happening kind of around here, right? And of course now we're standing up Aurora. By 2012, it was pretty clear that exascale was likely. That is, we had a scenario where we described business as usual. If we didn't do anything, would the world get to exascale? And the answer was, yeah, probably by sometime between 25 and 30, depending on your estimates. But there was a sense of, could we pull that in and accelerate that? So we definitely had the idea that it was possible. The vendors had stopped saying it was nearly impossible. The DARPA report suggested that it was going to be very, very difficult, but by 12, it seemed that this was likely to happen. What was less clear is how to do it. And this was a slide that I put together. Some of you, like Mike and others, probably remember this slide we were kicking around. We're trying to communicate to the community and the DOE that this was not business as usual, that we needed to organize ourselves differently. And we had these different strategies here. The bottom here, fast forward, these were investments in hardware, kind of more R&D hardware, and then green was more like NRE, this non-recurring engineering investment in hardware that was going to realize actual machines. And then we had the orange layer here, which was build out the software environment, starting from kind of research level software in the X stack towards an actual real environment that now has manifested itself under Mike's leadership into this great thing we call E4S, which I'll mention a little bit later. We had a notion that we're going to have to buy machines and how to do that. And it was going to be one machine, it was going to be multiple machines, and we had to figure out how to do applications. And this was all, this slide, of course, was before we created the Exascale computing project, but you could see in this conversation, kind of 2012, that we had the notion we had to do all of this and all at once. And this was bigger than any single laboratory, really bigger than any single organization. It was a joint effort between the Office of Science and DOE and the National Nuclear Administration, National Nuclear Security Administration, NNSA. And this was the blueprint for creating what later became the Exascale computing project. Now, if you fast forward a bit, at the time when we were thinking about these machines, this was before GPUs had really become a viable compute platform. And even as late as 2018, 2019, the thinking was that, well, we need to have some GPU machines, but maybe we should look at other technologies as well. But essentially, in the intervening years, this idea of a CPU-GPU architecture essentially has taken over. And even at Los Alamos here, with the Crossroads machine, is actually the follow-on machine has GPUs as well. So this gives you a sense of what was happening in the US. And this was, again, not one machine, but a whole series of machines from which we were learning things across the system, passing on. And users, if you're users on this system, you know it's an ecosystem that many people are able to use. This is a sense of what's been happening across the landscape. Now, we've been working hard on standing up our Exascale machine, the second one in the US. It's Aurora, lots of specs here. If you were at ISC, you heard some of these. I'm not going through the numbers. This picture's more interesting. This is somebody installing like one of the last blades into the machine. They have to use these cranes. These blades weigh about 70 pounds. And you can injure yourself. You can't really pick them up. You have to use a machine. And there's just thousands of these. In fact, our machine has like 10,000 of these blades. The red and blue is cool to look at. It's very photogenic. These are the liquid cooling pipes. So you might imagine the blue is the cool water coming in. The red is the warm water coming out. There's lots of new technology in Aurora. Here's some fun things. If you're a geek like, well, most of us in the room, this is the kind of stuff we consider fun, right? So we got a new generation of CPUs with high bandwidth memory, right? Intel decided to put high bandwidth memory in their CPU. That gives a significant boost for applications that are memory bandwidth limited, which has been really interesting to play with and figure out how to use that. Our machines also have a large amount of DDR5 memory, so normal memory as well. So how you mix those for CPU is really interesting. We've got, of course, Intel's new GPUs, codenamed Ponte Vecchio. I don't know what was going on with Intel when they decided to actually make the names that they announced these with. They called them Max. Max series, Max is just Max. I don't know how to, I guess I stole names from Apple. But the Intel GPUs are quite interesting because they're not monolithic. Inside the package are 47 chiplets built on 5 different process nodes. Some of those are made on Intel process nodes. Some of those are made on TSMC process nodes. Together, that's an integrated device in a single package. We have some very interesting storage system. It's a distributed object store. It's not a normal file system. And because we got rid of POSIX semantics in the file system, we have a huge amount of bandwidth available to us. This is driven with Optane memory and non-volatile NAND memory. But across the machine, we have about 30 terabytes per second of bandwidth, which is about an order of magnitude more than what we'd get if we used, say, just a normal file system. These things are implemented in these giant racks. They weigh 8,000 pounds. They're kind of, too big to hug. And the software stack is actually way more interesting than we thought it was going to be. I'll give you a little bit of this. So this is what a node looks like. I'm not going to go through this. I'm happy to give these slides to people. This is more just a high-speed tour. There's 6 GPUs on a node, all connected with a PCI switch. We have 8 network connections coming into that node that spread the bandwidth out. So there's 8 PCI devices, the 2 CPUs and the 6 GPUs, and a coherent switch, and it's all liquid cooled, of course, in a node. This is what our Sunspot system, this is our test and development system, looks like this. It's 2 of these racks. The big system was 166 of these racks on the right-hand side. That funny plumbing thing is it's called a virtual CDU. It's what manages the water and cooling. We have lots of those. Every set of 3 or so nodes have one of these systems that takes a huge amount of water and pushes it through. This is a really fun machine. Over Christmas, I didn't go anywhere. I stayed home, and I was the #1 user on this machine for about 2 weeks. It was a lot of fun. Everybody was gone, and lots of people on that machine. One thing that's interesting about our big machine is it's got over 80,000 endpoints in the network. This is about twice as big as our sister machine, Frontier, down in Oak Ridge. It's got 8 interfaces per node, huge amount of bandwidth in and out of the node. It's based on Hewlett-Packard Cray, HPE's Slingshot technology, which sits on top of the physical Ethernet layers. And it's got a 1D Dragonfly topology, which might mean something to some of you. And a large number of groups that connect everything together. This is the Deo system I talked about, and so forth. All right. So in 2010, when we were thinking about, there was a series of workshops, a number of you were probably at them, where we were trying to imagine not just the hardware for exascale, but what the software environment might look like. And at that point, it was pretty clear that message passing was going to work up to a few thousands of CPUs, 10,000 CPUs or something like that. But something else was going to be needed, particularly if we had fat nodes that had to control a lot of threads, vectors, and so on. So we had this terminology that we created called MPI plus X. And first started appearing on slides probably around 2010. And we knew MPI was going to be there, but we didn't know what X was. Right? X could have been many things. And it turns out that now that we've got these machines up, we kind of know what X is. And X is actually many things. And one thing that's really interesting for Aurora is Intel decided to create an integrated programming environment called OneAPI, which some of you have heard about, and I'm not really selling this. It's an interesting approach. They got this as an open spec, and it's an open implementation, so many groups can build against this. And it builds on top of C++. It's a very kind of minor extension on that, and then a lot of libraries. It's a 3-level abstraction set. There's a very low level called level 0, very imaginative name. And it kind of has all these components, and it fits into the Intel toolkit and so on. I'm not really selling Intel here. I'm just saying that this is the strategy that we worked on with Intel. And the nice thing about this is you can develop on CPUs and port over to GPUs. And in fact, the implementations of this run across all 3 flavors of GPUs that we have. So Sickle is what the programming model goes by from the Kronos group. But if you're thinking about that X and the MPI plus X, it's essentially these different options here up on the chart. That was pretty interesting. Here's how the stack sits. It sits on top of C++. Sickle is this kind of open spec developed by Kronos, and then Intel's is a slight superset sitting on top of that. So we have a large number of applications running on the system and many more that are being ported. And some of these were reported out at the ISC meeting. I just want to give you a little bit of a flavor. So we keep track of these by how well people are doing. Green is like really great, and orange is like not as great as we want. And so people are making progress. These are all applications that we're reporting on because they're either formally part of the Exascale computing project or our early science project. And at ISC, we reported out a bunch of these. I'll just flash a few slides up here just to say how we're thinking about these. Like here's one that we're very proud of. This is OpenMC. This is a Monte Carlo simulation environment that's being used for developing neutronics in small modular reactors. It's a Monte Carlo particle transport code. A lot of energy has gone into this, and the performance is pretty attractive. It's quite good relative to our sister GPU chips and good scaling. So this is kind of like the poster child. It's like the one we ask people to kind of reach for. It's a pretty good reflection of what the underlying hardware is capable of. Here's another one that's used in predicting plasma fusion structure and evolution. It's a gyrokinetic particle in cell simulation code. Again, it's got pretty good benchmark performance in terms of how fast it's working and good scalability. This is our cosmology code, Salman Habib and Katrin Heitman's code in their big group. Again, exascale code doing very well on this machine. Northwest Chem's a quantum chemistry systems doing quite well, and QMC Pack and so forth. So a lot of applications, electrodynamics, and we're very sensitive trying to, the Intel hardware has got a lot of capability, and we're trying to push as close to the theoretical limits in that hardware as possible as a way of making sure that ultimately the most science can get done in this machine relative to its theoretical capabilities. So, we're seeing pretty competitive performance, which is good. Given this is Intel's first really high performance discrete GPU, it's been very challenging, and some of you who've been watching the clock kind of know that. I mentioned Mike's effort and Lois Kerfman-McInnes's effort in leading the software stack for ECP. One of the great deliverables coming out of the ECP project is this thing called E4S, which is a software stack for extreme scale science. It's not specific to any of the exascale platforms. It's actually very portable. I don't have time to give a whole talk on this. Mike would give a much better talk anyway. But this is going to be one of the major accomplishments that comes out of the exascale program. And from an international collaboration standpoint, one of the huge levers that our colleagues in Europe and Asia can utilize to not have to reinvent the wheel. It's very, very open and very available. So what did we learn from exascale? Well, we learned that different groups were motivated differently. So dreaming about future hardware is kind of like appealing to this kind of audience, right? The scientific computing community gets excited about new capabilities, right? But if you want to go to, say, Washington or Brussels to raise money for these machines, that's not what gets people excited. What gets people excited there is what the impact is going to be from the science or the applications that you can do on this machine. And it took us quite a while, actually, in the US to figure out how to tell that story. And I would say that we never really found the single application that drove the investment in exascale. We're kind of finding it now. It's probably AI at the end of the day, but it wasn't what we proposed to drive this machine. The other thing that we learned, and this is, in hindsight, seems kind of obvious, but when you're raising billions of dollars, the exascale program, you include the ECP, was about $1.8 billion, plus the hardware investments, all told is about $4 to $5 billion over a decade and a half. When you start talking about these numbers, how you manage risk starts to dominate the conversation, right? If you're doing small-scale science, a few $1 million, you can fall on your face. You might get a ding on your reputation maybe for not succeeding, but the agency doesn't get penalized for that. But if you screw up on a few $1 billion, lots and lots of people are at stake, right? They're exposed. So as these things get bigger, risk becomes more important, and we've learned how to manage that risk. And this is probably the lesson, one lesson to communicate to the future generation. If you keep aspiring to big things, you've got to get good at all three of these things: inspiring your community, pitching it for dollars, and managing risk. So what are some of the post-exascale, post-game actions? There's things that we're doing, starting to do right now that kind of matter. So first of all, we've got to learn lessons from all of this and encode this in a way the next generation can keep going. We still have to actually fulfill the promise. These machines are just coming up and going into production, and all that great value to the country and to the world from this still has to accrue, and so we have to deliver that. And we need to protect and build on the investments in software. These software investments have been huge. There's never been a software project like the ECP that involves so many people and delivers so much value in such amount of time, and we have to build on that. We can't afford to recreate it, and we can't afford to lose it. So that we're trying to work that out, right? So, but there's lots of things that we could do, and lots of things we can do together, certainly with our colleagues. There's another list of things, right? As we start to turn on these machines and we start to see incredible performance in applications, we can start imagining workflows where we need that performance to actually make a difference in many applications. And we need to think about how to do that. Think of the exascale applications as elements and workflows. We're starting to see opportunities for AI connecting to applications. I'll say more about that in a minute. And we're also starting to see, and there were some talks here this week about this, where AI surrogates or even end-to-end AI replacements are going to complement traditional modeling and simulation. So there's lots of things that are in this end game. It's not really the end, it's like the beginning game of like the next phase. Here's just one little example that we're playing with. Let's say you have some kind of a simulation environment over here on the right, and you want to put up some kind of a virtuous cycle where an AI system, maybe driven by a large language model, can learn by observing what that simulation is doing in various ways, and to suggest improvements on the parameter space or whatever, and do this kind of management loop automatically. Right? We're starting to see prototypes of this. This is, I think, just the very, very beginning. All right, let's talk about exascale, or AI for a second. We're on the road right now, it's almost like deja vu, towards building a large-scale activity in what we call AI for science. It actually has several different names, but AI for science is how we originally started it. Now, why did we think about this? Over the last, well, about 6 years, actually we started thinking about this probably 6, 7 years ago, it started to become clear to us that we had all the ingredients for doing some really amazing stuff in AI. We just didn't have a comprehensive AI program, right? So we've got these incredible experimental facilities and supercomputers in our Department of Energy labs, right? We've got a huge amount of infrastructure for managing data, both classified data and unclassified data. DOE is the largest producer of both of these data streams. We have a huge foundation in science across physical sciences. DOE is the biggest sponsor of physical science in the US. We have the largest scientific workforce under one organization in the world. So we have the machines, the data, and the people, 3 magic ingredients for making progress in AI. We also have strong connections with vendors and industrial stakeholders. So it's like, gee, we have all the ingredients. Maybe we should take a look at what the opportunities are if we make a big move in AI, just like we did in 2007 on Exascale. So in the spring of 2019, 3 labs, my lab, Argonne, Oak Ridge, and Berkeley, my colleagues, we got together and we said, look, let's redo this 2007 exercise, except now we're going to focus on AI. We'll hold town halls. We'll get everybody together and say, you know, what do you want to do? Right? This is a lab-driven exercise. We invited our NNSA colleagues. All the labs came to this, and we had over 4 meetings, 1,300 people, and we walked through research across pretty much all the domains: biology, chemistry, material science, high energy physics, nuclear physics, climate, environmental science, et cetera, national security. And also the infrastructure, the mathematics, the systems, and so on. We produced a report, came out in spring of 2020, a couple weeks before the pandemic hit. And we managed to get a recommendation to the advisory committee for advanced scientific computing. They put together a subcommittee, worked really fast, and recommended that things move ahead. And at that time, we would use a slide like this. I actually used this slide several times during that time and say, look, what can we do right now? Well, we can build models that can predict properties of things without theoretical understanding or deep mechanistic models. We can just train from data, like materials and chemistry properties in particular. We can learn approximate solutions to inverse problems, where we have enough data that we can bootstrap inverses, like in phase retrieval and X-ray. And we can generate large collections of synthetic data using generative models to model interesting phenomena to measure how much of the physics we're actually capturing in our models. And this was like from 2009, right? And these are all things that people have been doing now for quite a while. So, of course, there was a pandemic, and everybody shut down. There was no planning. We also had an election in the US that pivoted everybody. And so a couple of years, really, no forward progress was being made on an initiative. And in the spring of 2022, we started agitating again, saying, look, something is needed here. Given the speed of change in AI and across the system, we really need to take a new look at this. So it makes it sound like we're just doing workshops and reports, but of course all this, we learned that this is essential to get the community kind of aligned. And so we decided to hold another series of town halls, but this time we did it slightly differently. We organized it with 6 national labs. So the NNSA labs were full partners this time. A lot had changed, right? In this interval, we got large language models, image generation, DALL-E, et cetera, stable diffusion. Open AI was used to fold 1 billion proteins from DeepMind's AlphaFold 2, right? Lots and lots of things happening. So we decided, let's take a new look at this and let's change a little bit how we want to do this. So back in 19, we had this as a future list. Like, we wanted to develop some kind of AI method that could combine, say, symbolic computing with data-driven computing so that we could build on the 400 years of mathematics and physics and so on that we learned to work on symbolically. We wanted to couple AI to automated experiments, right, so we could accelerate discovery. And we wanted to figure out, can we develop an AI in the future that would help us make fundamental advances in theoretical science, like plugging the holes in the standard model, or coming up with theories that might explain the evolution of life on the planet. So these were some harder goals. And so we decided to organize the second series very differently. We thought about what are big roles that AI could play in the scientific enterprise, national security enterprise, and the energy enterprise, that are not going to be every data set has a model. One of the reasons for that is that there's not enough humans on the planet to manage a model for every data set. That's just not the way it's going to work. So we came up with 6 areas, 6 different use cases of advanced AI that actually would target multiple downstream applications. So for example, this one up here on the left, predicting properties of things and using that to do inverse design. The idea here is, again, not a model for every single problem, but a master model that knows how to do inverse design across many domains, right? We don't know how to do that exactly, but we think it's possible. AI coupled to robotics for autonomous discovery. Again, this is starting to happen. It's grassroots. But instead of building a separate silo for materials and chemistry and drugs and biology, imagine doing that in a way that combines across all of that. And so on. Surrogates, AI for software engineering, prediction control of complex systems, and foundation models for making headway on knowledge more generally. And let me deep dive into here one. So everybody's pretty much up to speed on this idea of a foundation model, right? Sometimes called large language models, or recently being called generative AI models. But basically, you're going to train some model on some huge chunk of the internet, and you're going to do in a very simple way, and it could be multimodal. and then you're going to adapt it downstream to many applications. This is the business model of OpenAI. It's everything that's happening right now. And there's a number of reasons why this is an interesting model. It kind of gets us away from this idea of every data set has its own model. It moves us towards, at least conceptually, towards this notion of something like a artificial general intelligence. We're very, very far away from that. But an AGI is going to be more like this than it is going to be, say, a random forest on a single data set, right? And it creates an ecosystem. You can build hundreds or thousands or tens of thousands of applications on top of this kind of a model. So this is clearly an interesting direction, right? State-of-the-art models like GPT-4, which are probably between 1 and 1.7 trillion parameters, maybe in this 8-way mixture of experts model, if you've been following the news on that. These are models that are kind of 1% scale of a brain, right? Brain, you have about 100 trillion synapses. Parameter is not exactly equivalent to a synapse, but it's, more or less order of magnitude approximation. So a trillion parameter model is about 1% of a brain. These things are trained on trillions of tokens of data. Now there's multiple efforts inside the labs working on this. I'll say more about that in a second. What's interesting about this is that these models can do many things. They can summarize and distill knowledge, go from unstructured knowledge to structured knowledge. They can synthesize across many, many sources. We were in the break here, we were playing around trying to get ChatGPT to come up with common differential equations between 4 different areas of science. It was trying. It was not quite able to do it, but it's trying. They can generate plans and solve logic puzzles. And with more work, they seem to be capable of at least occasionally suggesting interesting theory to play with. There's this great paper preprint that came out a couple of weeks ago from MIT and Weizmann, and they have this great quote down here. It says, after experimenting with GPT-4 in our own research domains, materials, chemistry, physics, and quantum information, we find that ChatGPT-4 is knowledgeable, frequently wrong, and interesting to talk to. In other words, not unlike a college professor or a colleague, right? So if your colleagues are not anything, they're often wrong, right? You have to push the envelope. They made an interesting bet among themselves. They said this will be a valuable exercise if at the end of the week or so they were playing with this, they will take some of their experimental capability and apply it to the theory suggestions that came from the model. So they're doing that right now. So what we're trying to figure out is how would we leverage what the broader AI community is doing here, right? Like OpenAI or DeepMind's new model called Gemini, which is supposed to be even better. Right, so they're building systems like this, general purpose stuff. I mean, they do have a little bit of science in there. ChatGPT-4 actually knows a fair amount of science. But we're imagining that a model in the future might actually have a role like this. It might be actually in the center of what we want to do, and either directly or indirectly help facilitate these different models, right? Either by generating and managing models, like the way that AutoGPT might do it, or some other way we haven't invented yet. But maybe it's at the center. And if it is at the center, we're going to have to solve some interesting problems. One is that we're going to have to figure out how to take real scientific data, not just papers scraped from the archive, right? But real huge data sets from biology, chemistry, material science, physics, so on. These are multimodal. Some of these are fields, strings, sequences, all kinds of stuff. Figure out how to train models. And then the downstream adaptation is not for general use cases, writing law briefs or whatever, but for our kinds of problems, right? Discovery, digital twins, and so on. So how are we going to do that? We've been thinking about this. So I'm going to go through this part very quickly because I'm a little bit running behind, but large language models are already being used in many scientific domains. There was a paper a year and a half ago on using this to design proteins. Our group, where's Arvind? Arvind's right or somewhere, leading our group in building a language model called GenSlim that won the Gordon Bell Award at supercomputing for designing proteins, particularly designing or discovering future variants of COVID, but it's a large language model underneath, almost exactly the same code as you would train a GPT-type model. We're thinking about, is it possible to actually combine many of the use cases that we're working on today into a single model? Here's some evidence that it might be possible. The blue line are the model-specific cases, and the yellow and the orange are attempts at combining these things in a single language model. So we're very close to the performance of our special purpose models. Now, lots has happened since 2019 when large language models weren't really on our radar screen, right? Some of you have probably seen this chart. This is a really interesting kind of phylogenetic tree of language models. So back in 2019, at the bottom, people heard of BERT, right? There's lots of variations on BERT. GPT kind of came out. It was not that interesting. OpenAI was not that interesting. OpenAI was making a big bet on language models that they could scale things up. It wasn't until GPT-3 came out that it started to get really interesting, that these models started demonstrating significant emergent behavior. And all of a sudden, there was a Cambrian explosion, right? Of everybody realizing, oh my, there's maybe something here. And of course, GPT-4, ChatGPT came out in this kind of halo of lots of groups trying to replicate that. There's no sign that this is slowing down. In fact, it's accelerating, right? Most capable models today, the three top models, are of course private, closed models. Here's a so-called leaderboard kind of chart. What's interesting here is how they've scored them using the ELO rating. So ELO was the rating that's used for scoring chess grandmasters, right? And so a 100-point difference in the ELO rating means that the upper scoring one has a 64% chance of beating the lower scored one. A 200-point gap is a 70+% rating, so on. So this ELO rating is kind of interesting. It's also used to score sports teams and so on. It's a way of comparing things. So the top three, Claude is by Anthropic and ChatGPT-4 are very close, right? GPT-3 Turbo is a smaller model, but also not bad and much cheaper to run. And then all these open models that are quite a bit below that. Now, open source models are pretty hot right now. There's every week or so, there's a couple models popping out. There hasn't been any open source models at the scale of GPT 3.5 yet. The most interesting one that came out recently is Falcon 40B. And I'll describe this one because this one is kind of blew everybody's mind. So this was trained on AWS from Abu Dhabi. So it was a product of the Technology Innovation Institute. It was trained on 384 GPUs over about, 40 days, I think. Here is one of the standard questions I use for evaluating this. I ask it, which proteins interact with P53? P53 is a oncogene. It's a gene that helps repair DNA damage and prevents cancer. And of course, early open source models had no idea how to answer this question. This one actually does pretty good. This is completely open. You can download it. In fact, I have it running on my laptop. So this is a shift that's happening, right? So a couple years ago, a number of us were pondering this landscape, and we thought to ourselves, well, we need to organize ourselves, not just in terms of building a DOE program, but we need to understand, we're going to have these exascale machines. We need to understand how to approach this notion of building, say, a trillion parameter foundation model for science. And so we started creating a consortium. It's got a couple different names, but TPC is what we're currently calling it. It's got major vendors, but pretty much all the labs. There's ... there, all the NSA labs are part of this. Universities, RECON is part of this, Memorial Sloan Kettering Cancer Institute, the Allen Institute for AI, and others. Here in Europe, the Barcelona Supercomputer Center, LRZ folks, others are part of this. And we're trying to really create an environment where people can discuss, try to understand how to work together to make it possible to build these models. And what's really important to understand here is building a useful engine for science is more than just training a single model. In fact, if you listen to the Microsoft Build conference a couple weeks ago, Andrej Karpathy gave a great talk there where this is one of his slides, where he says, well, there's really 4 stages. There's this pre-training, everybody thinks about this. But to get a model that's useful in kind of chat scenarios, you have to do some supervised fine-tuning, some reward modeling, and finally some reinforcement learning so the model gets aligned with being useful for humans. Sometimes the model, if you push it through this pipeline, you add the word instruct on the end of it. It comes from the OpenAI paper. So there's been some initial hackathons, test shots. We're trying to organize this in a way it's vendor neutral. We will build a series of models at the same time. You're always building kind of small models to debug your process as you're working on big ones. There's a lot of parallelism here, a lot of low-level optimization. These things are huge compute tasks. On the left here is GPT-3 that was trained in 2020. It took about 4 million GPU hours to train that model. It was trained only on about 300 billion tokens. This is back when people thought that you'd train a model on roughly the same number of tokens as it had parameters. Llama, which many of you have probably heard of, came out of Meta, was trained using a different scaling law. So it was a 65 billion parameter model that was trained on about 1.4 trillion tokens. So many, like an order of magnitude more data. And it reflects kind of a different understanding of scaling. And it was about 1 million GPU hours, right? And these models are small compared to the trillion model. One of the bigger models, Palm, which is a Google model, about 500 billion parameters, was trained for 29 days on 4,000 TPUs. 4,000 TPUs sustains about an exaflop in BFP16. So you should be thinking in terms of order trillion parameter model is probably on the order of a couple of months using an entire exascale machine, right? So these are models that are not going to be trained by one small research group. They're going to be trained by whole teams of people. Just to put it in your head, the training cost right now, best kind of simple estimate, rule of thumb estimate is it's 6 floating point operations per parameter per training token. So if you have 1 trillion parameters and you're going to train on, say, 10 trillion tokens, you can do the math to estimate how many flops, and you can then divide by the scale of your machine. You know, this is going to be somewhere in the 1 to 3 months on exascale, and then all that downstream work. So this is something that's going to consume maybe a quarter of an exascale machine, and then you're going to have to evaluate it. So these are not going to be, you're not going to have 100 groups doing this. This is going to be a major effort. Just want some math in here. I'm going to skip over this. So there's, we have to work on pre-training. These models actually, when you train them, are unstable. They crash. You have checkpoints. You restart them. You edit them. It's very hands-on. One of the big tasks is doing model evaluation. There was a paper last year, very cool paper called Big Bench. It's one of the biggest number of author papers on computer science publications I've ever seen, 400 authors, 130 institutions. This is like a high-energy physics paper. And they built 200 evaluation tasks working together to evaluate these models. And we're going to need to do something like that for these deep science applications as we go forward. How we structure scientific data in a way that these models can learn relationships, still pretty open. The multimodal issues are wide open. How to actually include representations of different domains is really, in an inclusive way, is going to be challenging. And a lot of issues having to do with how we might release these models or how we might work on AI safety or bias and so on. So many, many research topics. One way we're thinking about this in the DOE context, this comes from a talk some of us gave last week in Washington, is something like this. This is just that same diagram now just mapped into our world, right? So a lot of training on general things, because the model has to kind of generally understand the world, training on the science data sets as you saw before, sitting on top of our exascale machines, probably producing a couple different versions, right? 2 or 3 different versions, maybe one that's specialized for national security, one that's specialized for open science, and then devising some way of specializing. This is a huge undertaking. Now, one of the things that's become clear is large language models are not yet very deeply probed. This was a very interesting paper. The title doesn't convey the interest of this paper, but it says, can large language models democratize access to dual-use biotechnology? What do they actually do in this? So this is a group at MIT, Harvard. They got students together. They did an exercise. It was 1 hour. 3 different groups of students. These students were not experts in biology, not experts in computer science, not experts in AI. And they asked them, they said, they tasked non-scientist students with investigating whether LLM chatbots could be prompted to assist non-experts in causing a pandemic. Right? In 1 hour, chatbots suggested 4 potential pandemic pathogens, explained how they can be generated from synthetic DNA, using reverse genetics, supplied the names of DNA synthesis companies that were unlikely to screen the request. Fascinating, right? And it recommended that anyone lacking the skills to perform reverse genetics engage a core facility or contract research organization to actually carry out the work. Okay? Just let that settle in your head for just a second, right? We've got 100 million people. When ChatGPT-4 jumped on the awareness, right? It was the fastest adoption of any internet application ever, right? Just exponential growth, over 100 million users. People are going to try all kinds of things with these models. We don't even have a systematic way to assess what a model knows. We don't have a systematic way to assess whether or not there's hundreds of examples like this that somebody could actually do. So there's, I'm not trying to make this into a dark talk, but we're going to have to get pretty serious about understanding what these models are capable of doing, devising methods for screening, evaluating, and so on. So I mentioned this concept for a large-scale program, the AI initiative, to carry out this vision. Roughly, the concept that we're putting together looks like this. It has a cross-cutting effort on the basic research to figure out how to assess these models and to assure that they're safe and reliable and trustworthy and so on, particularly in scientific and high-value applications, right? A middle part that's doing the lifting across all these application domains, cross-cutting AI technologies so that we build a stack that is going to be transportable between our platforms so we don't have silos, so building on top of the E4S experience, right? And then we're going to have dedicated access to machines and data sources at a scale that we haven't imagined before. We run our big supercomputers kind of as user facilities where people propose work and so on. But for AI like this, you're going to have dedicated exascale platforms. So, if we're successful, in 10 years, the world could be very different for how we do science. Let me spend a few minutes talking about quantum and Zeta before we finish up. Quantum is, of course, in the press. Governments are vying for quantum sovereignty, I guess you could call it that, local indigenous quantum systems and so on. That's captured people's imagination for a long time. And the question is it going to ever emerge in a way that we can do real science with it? That's the question I'm trying to ask. See pictures of these things? Beautiful gold-colored cryostat devices. So the real question from an international strategy around science, advancing science through computing, is quantum, is it going to contribute, right? Can we resolve if in our lifetime quantum computers are actually going to contribute meaningfully to solving the problems that people actually care about, right? Like many of the problems we're aiming the AI at, right? Faster or more efficiently or easier than classical machines. That's my kind of test. Current machines clearly can't do this, right? They're small, noisy, program them writing circuit diagrams. I mean, it's kind of crazy. We lack a good number of killer apps, right? And I mean by killer app here, you read Dorson's paper, of course, we need problems that have super polynomial or exponential potential speedups for all kinds of reasons. And we're going to have to find out how to integrate any successful quantum systems into our ecosystem in some systematic way so that we're not just siloing by different technologies. If you don't read any other papers about quantum next year, I suggest you read these two, not because they're easy to read, but because they're by two rivals, and they're published about 3-4 years apart, and they kind of make different ways of claiming. So the first one on the left was the Google paper in 2019. In fact, it came out the same day we were doing our 4th AI workshop, where they claimed quantum supremacy on a 53-qubit machine, essentially solving random quantum circuits. Was not well received by certain quarters, particularly IBM and others, because they made some very bold claims about how it was the same problem would take 10,000 years on Summit and so on. Various groups had subsequently shown that they can more or less approximate that problem or solve it much faster than that. Last week, this paper on the right came out. It's from IBM. This is still not a problem that anybody wants to pay money for, but now they're solving at least a real scientific problem. This is an Ising problem, spin glass problem. And they did an incremental series of scaling studies to show that at the highest scale, and based on their methodology, they were probably getting an answer more accurate than the classical machines. Not faster than the classical machines, or anything like that, but more accurate in a larger configuration. And they're trying to claim that even before we get strong error correction, there might be some utility of these quantum machines. So it's a partial step in the right direction. Now, when I think about these, I think about real targets that we might be willing to raise real money, whether it's commercially or from governments, to actually work on this. And the targets are kind of in this bucket. The first one is quantum simulation. And the reason for that is that we know current methods for accurately simulating the electronic state of certain systems, molecular systems or solid-state systems, don't scale well classically. And quantum machines, we can prove that they scale better. So that's one application. There's others that people talk about, quantum optimization, maybe exploring, black hole dynamics and so on, and maybe algorithms research, but I'm going to focus on simulation here for a second. So there's another paper you should read. This is a nice Swiss paper. Thought to put a Switzerland paper in here. This is a paper where they basically propose an approach to use quantum computing to solve electronic structure problems for catalysts, something that people actually care about. And the reason I don't expect you to get much out of this other than there's maybe two things to take away from this. First of all, the workflow has a quantum computer in it, but also a very significant amount of classical computing. In fact, all reasonably interesting quantum algorithms are hybrid algorithms. Quantum machine does part of the lift, classical does a part of the lift. Just keep that in mind. The second thing is they're trying to work out how many qubits they need, right? Measure of how big the quantum system is. And what they'll say here is how many gates, that is how long the computation has to run. Right? So for this problem, this one of accurately estimating the electronic structure of a catalyst, which is worth billions of dollars of revenue if you actually get the right one, needs thousands of qubits, reliable qubits, running billions to trillions of gate. Okay? Thousands running billions to trillions. In fact, over and over again in the literature, real problems have these estimates. I'm just putting the numbers up here. Logical qubits. These are reliable qubits, qubits that don't have errors, right? We don't have qubits like this today, but, and the Toffoli count here is how many gates, how deep the circuit is, or how long the circuit has to run. So you've got thousands of qubits, billions to trillions, some of them 10 trillion gates. Even the guys working on, so those papers are not specific to any given technology. This is just the algorithm. PsiQuantum, which are one of the very interesting groups working on this, have put out a number of papers comparing their technology to the superconducting and the ion trap systems doing similar things. This particular paper is focusing on factoring a 2,000-bit public key used in internet security. And their estimate here is 6 billion gates on 6,000 qubits. And if you look at other systems, similar numbers, different total times. So let's just do some math here, some back-of-the-envelope math, right? We're going to need machines that have thousands of virtual qubits. These are reliable qubits you can compute on day in, day out. They need to run programs that have a circuit depth of somewhere between, say, 10 to the 10 and 10 to the 12. The way to think about circuit depth is like how many, think of it like your program is unrolled and you're just measuring how long you're going to run the program. And so a typical estimate for the time to run a single gate is maybe a microsecond. So if you just do some basic math on here, we're talking about 1,000 virtual qubits running for 2 weeks, okay? Now, unlike a classical machine, during that 2 weeks, there can be absolutely no failure. You lose the quantum state, you start over again. There's no checkpoint. No checkpoint is possible. Okay? So that's kind of like what it's going to take to be competitive. Now, there are companies, lots of smart people working on this. IBM's got a great roadmap. We're very happy working with these guys, right? They just put out 400 qubits, that great paper we just talked about. They're trying to see how they can scale it up, form clusters of it. Maybe by 2026, they're maybe 10,000 qubits. Maybe by 2033, they're talking about maybe 100,000 qubits. 100,000 physical qubits would yield maybe 100 reliable qubits, so order of magnitude short of what we need. Here's a similar kind of chart for a couple different technologies, but nobody is talking about quantum having 1 million. Well, the only company that's talking about it is PsiQuantum, maybe in the 2030 timeframe, 1 million qubits. Okay? So what would it take to actually accelerate this? Well, first of all, we have to find more algorithms. We don't know how to do that exactly, but we do know that AI can discover new algorithms. DeepMind had an example of that. We need to probably build 2 or 3 machines, different technologies, work out how to scale these up and so on, right? Let's skip through this. I talked about how real quantum systems have a classical component, a quantum component, right? So one thing I mentioned this, there are likely to be mixtures. Almost any formulation of a quantum computing problem has this kind of cycle where you're going to structure things classically, run some quantum, structure them classically, and so on. Doesn't matter what you're running. Now, what might this cost? Well, last year, the average retail price for running on a quantum computer that's in clouds was about 5 cents per qubit second. And you can do the math for these problems that I mentioned. So if you're trying to solve a electronic structure of an enzyme, right? Using the estimate that we have here, they're talking about some large number of qubit seconds. That's about $5 billion at the current price. Fixing nitrogenase, room temperature nitrogenase, nice problem to have. Hundreds of billions of dollars of industry and agriculture based on this. That's a $20 billion problem at today's costs. Factoring composite key, about $20 billion, okay? So at the current price, nobody's gonna pay, right? Now, the question is, how fast can the price come down? Assume that the technical solutions are solved in the same way that we solved them for classical computing. Once before in history, we had a factor of 10,000 reduction in cost. We need to get this cost down by a factor of 10,000 to make it competitive with current exascale systems. In other words, spending a few $1 million for a couple of weeks. That took 20 years in transistors. So if we assume the same rate of progress, now qubits are harder than transistors, but it's probably not likely that we're going to get to this cost point until sometime in the 2040s. And this now closes the loop here. In the meantime, we're going to have classical systems. And I know, Mike, you need to get me off, and I'm almost done. So we're going to have to make progress on classical computing. And there's all kinds of ways we can do that. I just want to throw up a couple of high-level questions to consider. The The market's being driven by AI. Traditional simulation needs high precision, AI doesn't. We're going to have to get more clever on how we combine those things. Surrogates are showing great progress, but whether or not surrogates will be the dominant way, we don't know, right? There's only 1 or 2 papers out there, people trying to estimate this. There's a paper from China where they estimated a system, and I just did the math trying to show how much we would have to improve each of the parameters to achieve this by 2035. Some of these have incredible annual rates of improvement that we don't know how to do, right? So let me just stop here. So this is my kind of summary slide. So we're going to push towards AI for science. That's going to, by necessity, scoop up a lot of HPC technology and hybridize with it. We're going to make a long-term push on hardware towards Zeta scale. We have to do that. Quantum is not going to rescue us anytime soon. And the AI applications, while they're great at advancing low precision alone is not going to serve the science. So we have to find the right balance there. It might be possible to think about special purpose hardware in the next couple of years. So for these quantum chemistry problems, that's a good target for quantum computers. For AI, maybe thinking of a machine that could construct a system of 100 trillion parameters, that would be a brain scale system. We're a couple of order magnitude away from that. So with that, I say it's easy Q, but it doesn't mean that making quantum work is going to be easy. But if we can just align with this trajectory, I think we have a great future. So let me stop there.